Okay, so today we're starting Unit 2. Unit 2 is based more in algebra and geometric applications. So we want to start looking at some of our basics of geometry. And in geometry, our most basic unit in geometry, our most basic object in geometry is this thing right here. It's called a point. And it is nothing more than a location. But everything in geometry is created from that point. If I take that point and I move it in a single direction, drag it, or however you want to call it, what I have created is a line segment. Now, a lot of people call it a line, but a true line goes on forever in both directions. They'll ask you, what's the measure of the length of that line? Well, you can't, because all lines go on infinitely, so they have an infinite length. So when they say measure the length of a line, they're usually talking about a line segment. The length of that line segment is equal to the distance that we moved it. It's also valuable to note that we move this in one direction. It is one-dimensional. So next, we're going to take that line segment again, and we're going to move this line segment again. But to define the motion, we need to define a concept called perpendicular. A right angle is a 90-degree corner. Two lines that intersect at a square corner or a 90-degree angle and make a right angle. To be perpendicular, you have to form right angles, but it's a little more powerful than that. For lines, yeah, being perpendicular just means they form a right angle. But perpendicular can apply to things other than just lines. I could have a line coming out of the surface of this paper, the screen, to be perpendicular to the screen or the computer paper, whatever. It has to make a right angle in every possible direction. And that's what perpendicular means, is it makes a right angle in every possible angle you could measure. So anyway, the reason we had to talk about perpendicular is now back to this line segment. We moved it in one direction. Now we need to move it in a second direction that is perpendicular to the first one. Now, we're so used to seeing geometry in two dimensions on a flat surface or flat piece of paper, it really looks like we only have two options. You either go up or down. But I could pull it towards us, we could push it away from us. There's several directions that are perpendicular to that first one. We're going to choose to go just down with it. So we moved it perpendicular. Now, if you think about this, if you think about it as like maybe taking a stick in the sand and pulling the stick across the sand, it's going to trace out a rectangle. Of course, since it's perpendicular, these are all right angles, right? The area of that rectangle depends on the length of the original line and the distance that we move that stick. The distance is often called a width. Notice here, two directions. It is two-dimensional. When you hear the term two-dimensional, they use something called degrees of freedom or directions of freedom to move. They can move in two distinct directions. So, of course, the size of that rectangle is determined by that length and that width. We'll talk about area later on in the course, but area would equal that length times the width. So back to my point. Instead of pulling it in a single direction and stopping to make a line segment, we can pull it in a single direction and keep going forever. That little arrowhead on the end means it keeps going in that direction forever and ever. This forms something called a ray. A ray is completely defined by its starting point and then any other point on the line. Or on the ray, I should say. Any other point on the ray. When I name a ray, let's say this is point A and point B. I'm going to be really creative with my names. It has to be named ray AB. That starting point has to be the first one named. If I were naming my line segment up here, let's say this is C and D. Line segments must be named for their endpoints, but I can name this line segment CD or line segment DC. There's no direction to it, so I can go in either direction. Well, if I create this ray, then I come down and I create another ray. I go back to that same starting point, point A, and I create another ray by pulling, oops, pretend it's straight, by pulling that point in a different direction. I've created a second ray, but I've also created an angle. The measurement of an angle is what's called a difference in direction. We're not going to dwell on this definition too much, but I'm going to show you what it means. This is the original definition of an angle, and it comes from navigation way back when. A navigational system, basically the compass, starts with 0 degrees here in the east direction. Go to the north direction, that is 90 degrees. The west direction is 180 degrees. South direction is 270 degrees. So my first ray, well, let's just do it like this. It may look like that. The direction of that, of course, is measured from the 0 point, how far it goes. Let's say that is at 23 degrees. That's its direction. If I draw a second ray, I'll put this one in blue here, and that one has a direction of 65 degrees. The angle, now they have a common starting point here. They both start at the center of the graph. The angle between them is defined to be the difference in those directions. 65 minus 23, which would be 42 degrees. This common starting point, by the way, is referred to as a vertex. Now, this definition of the measurement of an angle being defined as directions was a lot more useful back when navigation was more common, where many people, a large portion of the population, knew how to navigate, knew directionals and angles and stuff like that. These days, it's not so much sort of a common piece of knowledge anymore. So we've kind of altered our definition to make it a little more standard. If I have something and I make a complete circle, how many degrees have you turned? 360 degrees. If I make, bless you, turn so I'm going back in the opposite direction, how many degrees have I gone? 180. How did you find the 180? It's half a 360. We went half a turn. Half a 360 is 180. What if we turn and go at a right angle or square corner? That's 90 degrees. Again, we made a quarter of a turn. 1/4 of 360 is 90 degrees. By the way, a 90-degree angle is a right angle or square corner. That is usually signified by putting a square or a box in the corner. to signify that it's square. So angles have become defined by the fraction of a full turn. And so that for a fraction of 360 degrees. If I have an angle that is listed, I'll use the same, 42 degrees, that means that is 42 3/60ths of a full turn. Any questions? Okay. So now let's look at some special relationships with our angles. So we take an angle here, has a vertex. And I'm just going to give you that angle is 38 degrees. Now I'm going to go back to the vertex of that angle, and I'm going to create a third ray now. It goes like this. And this, of course, makes a second angle here. And this second angle, we're going to say, is 51 degrees. What we have created here is something called adjacent angles. Adjacent angles share a vertex, and they share a common side. Now, it's possible for more than two angles to be adjacent. I could make another ray here, and now they all three share a vertex, and pairwise they share common sides. So any two of them will share a common side. Adjacent angles, I'm going to do that one. Adjacent angles have the property of being what we call additive. We can add them together. So if I wanted to know the size or the measurement of this whole angle here, I can add together the two smaller angles as long as they are adjacent. 38 degrees and 51 degrees is 89 degrees. Now, we've said that subtraction is a byproduct of addition. That they're the same operation, one's going forward, one's going in reverse. And because of that, let's say we have something like this, where this is 99 degrees. And this angle out here is 151 degrees. And I want to find this angle here. How could we find that? Well, if angles are additive, it implies they're also subtractive. I can subtract them. Or if you wanted to think in terms of our solving equations that we talked about a little over a week ago, if that's x, x plus 99 has to add up to 151. You can see where the subtractive property comes from the fact that they're additive. So how do I find x? Subtract 99. Very good. So x equals 52 degrees. Any questions so far? So that's one of our relationships with angles. If they share a common vertex and a side, being adjacent angles, we can add or subtract them to find missing pieces. Next relationship I want to talk looks like this. So I have intersecting lines, and if I tell you that this angle here is 57 degrees, what can we say about this angle over here? Heard somebody say it. It's also 57. Well, why? Well, remember, if you think of this as being rotations, as an angle being a fraction of a full rotation, if this line here started out on top of this one, it had to rotate to make that angle. Well, this end of the line had to rotate the same amount as the opposite side. It has to rotate the same amount around this center of rotation on both ends. The other way we could look at it, and we're going to come back to this in just a second. This is what we call vertical angles, by the way. Vertical angles are across from each other and intersecting lines. But another way we could look at that is we could look at special pairs of adjacent angles. If I have two adjacent angles that add up to a straight line, let's see, I know this here is 79 degrees. How much does this angle have to be? Well, a straight line is how many degrees? 180. So that's 180 total. If I call this y here, 79 plus y has to equal 180. So 180 would be, subtract 79 to find a missing angle, y equals 101. So this is 101 degrees here. When we have two angles that combine to make a straight line, they're what we call supplementary. They don't necessarily have to be adjacent angles like I drew them here. Any two angles that add up to a straight line or add up to 180 degrees are supplementary. If they're actually adjacent angles like this, there's a stronger term for them called linear pair, but we're not going to worry about that term right now. Well, another option is we'd have two angles, not necessarily adjacent, but I'm going to draw them adjacent, that add up to 90 degrees, a square corner. If I know that this angle here is 68 degrees, what's this one have to be? 22. How'd you come up with that? If I call this angle Z, 68 plus Z has to add up to 90, a square corner. So I'd subtract 68. Z does equal 22 degrees. Now I don't have to set up the equation. You could just look at that and say, hey, they add up to 90, so 90 minus 68 is 22. This is what we call complementary. Complementary angles add up to 90 degrees or add up to a right angle. Now, if you're anything like me, when I first learned supplementary and complementary, I had a hard time remembering which one was 90 and which one was 180. So I remember them this way. Complementary angles add up to a right angle. You get complements when you're right. So if I give you an angle of 43 degrees, and I ask you, what is its complement? What are you going to tell me? $47 degrees. How'd you get that? Yeah. Okay. Well, so you know they add up to 90, right? So 90 minus 43 is 47. So why are we spending so much time talking about this? Well, I'm going to go back up here for a second. The vertical angles. So now knowing this about my supplementary and complementary, what do I know about my 57 degrees over here and this angle here? They have to add up to 180. This is a straight line, so they are supplementary. They add to 180. So if this is 57, this is 180 minus 57, or 123 degrees. Well, now that I know that, what about this angle and this angle? Yeah, this is also a straight line, so those two have to add up to 180. So I can do 180 minus 123, and I get 57 again. There's a rule in math that if you have one number, if there's two different things you can add to it to get the same total, they have to be the same number. Similar here. If I have an angle, if I have two different angles that are both supplementary to that angle, well, they have to be the same angle. So these two here, my vertical angles, must always be equal, because they both have to be supplements to this angle. And there's only one supplement to that angle. So our objective here might look like this. If I have two intersecting lines and I label those angles 3x and x, and I say find the angles. To do that, I first must identify what is the relationship between those angles. Either they add up to something, they subtract to make something, or they're equal to each other. Are they equal to each other? No. In this case, they will add up to make a straight line, so it's supplementary, so 180. So 3x plus 6x has to be 180 degrees. Now we just solve the equation. What do we have to do? Combine 3x and 6x make 9x equals 180. And then divide by 9. X equals 20. Am I all done? No, 20 is my answer for x, but it doesn't answer the question. The question asked, find the angles. So if x is 20, this angle is 3x, or 3 times 20, or 60 degrees. This one is 6x, or 6 times 20, or 120 degrees. Now I can double check to make sure I didn't make any silly mistakes. Do those two add up to 180? They sure do. Looking at this one, I have two angles I'm asked to find. I'll just call this angle A and angle B. When I'm looking at those two angles, what's the relationship? Do they add up, do they subtract, or do they equal each other? They have to add up. A plus B has to give us 71 degrees because they're adjacent angles. So A is 5x plus 4, plus B is 2x plus 3, and they have to add up to 71. So now what? 5x and 2x make 7x. 4 and 3 make 7 equals 71. It's going to turn out to be ugly. I screwed up. Subtract 7. 7x equals 64. Divide by 7. Really haven't done fractions yet. But if I divide that by 7, it's going to come out to be x equals 9.142857143 approximately. That didn't work out real well. I screwed up making the problem, but then we put that back in for x, and we'd have to solve the problems. We haven't worked with decimals yet, so we're not going to pound on that right now. Any questions? Okay, let me try to give you one that actually does work out. How's that sound? In your notes, see if you can find the two angles here. See if we make that work. So what's the relationship here? They add up to 90 degrees. Good. So 7x plus 14 plus 3x minus 4 equals 90. Could have been the other way. You could have had 3x minus 4 plus 7x plus 14. It'll work out the same. What do we do next? Yep, 7x and 3x make 10x plus 14 and a negative 4 make 10 equals 90. And then subtract 10. 10x equals 80. And then divide by 10. So x equals 8. All done? No, what do we have to do? We know that x equals 8. We have to come back here and find the angles now. So this is 7 times x becomes 7 times 8 plus 14. 7 times 8 is 56 plus 14 is 70. This is 3x minus 4 becomes 3 times 8 minus 4. 3 times 8 is 24 minus 4 is 20. So 70 degrees and 20 degrees. How many of you got 70 and 20? Or 20 and 70? Perfect. What's the relationship between these two? Careful. Here they don't add up. They have to be equal. This angle and this angle have to be equal to each other because they would both be supplements to this one. So 5x minus 7 equals 3x plus 13. To solve this one, of course, we see that we have a variable on each side. So what do we have to do? Yeah, we got to get rid of one of them. Right? Normally, we're going to get rid of the smallest one because it avoids us working with negatives. The smaller one is the 3x. So to get rid of it, you think of this equation as being a balanced scale. We're just going to literally take it and pull it off and throw it away. And mathematically, we do that by subtracting. Subtracting 3x, it's gone. Subtract 3x over here as well. The only thing I can take it away from is the 5x. That would leave me with 2x. So 5x minus 3x is 2x. We still have the minus 7. Over here we have just the 13 is left. Then what? Add 7. 2x equals 20. And then divide by 2. X equals 10. Now what? We have to solve. We have to go back and find our angles. X is 10. This is 5 times 10 minus 7. 5 times 10 is 50. Minus 7 is 43. Same over here. This becomes 3 times 10 plus 13. 3 times 10 is 30. Plus 13 is 43. Any questions? Let's say we try some. Find the two angles for me in your notes. What's the relationship here? add up to 180. Very good. So it doesn't matter which one I put first. I'm going to put 4x minus 2 first. Then the 12x plus 22 second. Then what? Combine 4x and 12x make 16x. What else? Negative 2 and 22 make positive 20. Over here we still have the 180. And then subtract 20. So 16x equals 160. And then divide by 16. This equals 10. Then what? Well, we put 10 back in here. 12x becomes 12 times 10 plus 22. 12 times 10 is 120 plus 22 is 142. So this angle here is 142 degrees. Do the same down here. Put in 10. 4 times 10 minus 2. 4 times 10 is 40. Minus 2 is 38. So this angle is 38 degrees. How would we double check this? Add them together and see if they come up with 180. Do they? Yep. Yes, they do. Good. So for this one, we have an angle is 118 degrees. I have another ray in it here that forms an angle here of 86 degrees. Oops, sorry. Yeah. I did that wrong, but we'll make it work. This angle right here has to be 4x minus 4. Find the value of x. What's the relationship here? This one's way simpler than it looks. These two have to add up to 118. So 4x minus 4 plus 86 equals 118. So there's nothing to change with the 4x. But we have negative 4 and 86 make a positive 82. And now we can solve for x. So subtract 82. 4x equals 36. And then divide by 4. X equals 9. And all I asked you for there was to find the value of x. You could have, by the way, just said, hey, 4x minus 4 has to equal 118 minus 86 is 32. And you could have gone with it that way. That'd be just fine. So here we have an angle that's 39 degrees. This angle here is 3x plus 5. And let's see, over here we've got 8x plus 4. I want you to find this angle right here. What's the relationship here? Well, 39 plus 3x plus 5 equals 8x plus 4, correct? So the 3x is going to stand alone. Got 39 and 5 make 44. Now once we've combined what we can on each side, we still see that there's a variable on each side. So we have to get rid of one of them. Which one are we going to get rid of? The smaller one, the 3x. So that's gone. We have 44 equals 8x minus 3x is 5x. And we still have plus 4. Now we're just going to solve it. Tell me what to do. Subtract 4. So 5x is equal to 40. And then divide by 5. X equals 8. Now I asked you to find this angle. So you have to come up here and put 8 in for x. So this is going to be 3x plus 5 will be 3 times 8 plus 5. 3 times 8 is 24 plus 5 is 29. So that is 29 degrees. Any questions? Okay, it's about time for a break, so let's go ahead and take our break. It's 4:19. Let's shoot to come back at 4:29.